FSE 100 group project presentation, Team 8, Mario Party 5. Introduction. Messy homes are an all too common annoyance, especially when children and pets are involved. Our team is developing a solution to that problem. According to the United States Census Bureau, the average family has 3.23 people in 2019. Of those families, 21.2% had children under the age of 6. Additionally, another large segment of the population have pets in their homes. According to the American Veterinary Association, there are approximately 67% of American households who have pets, to include dogs, cats, and birds. Pets and children are messy. They leave toys around the house, spill food and drinks. In the case of pets, there may be instances of vomiting or accidents on carpet and flooring. In addition to the intended customer, parents and pet owners, other individuals impacted by this problem may include elderly people and those who have medical constraints that prevent them from tidying up in a traditional sense. These individuals have limited abilities, must be considered in the design along with the target customer. Stakeholders must also be considered in the design to ensure that project meets all of the requirements and is created within the allotted timeline and under the desired budget. Currently, the robot style to solve the issue is picking up off the floor is limited to what it can pick up by its small size and design. It is comparable to a regular vacuum cleaner when looking at the particle size of objects that can be collected. The main benefit of this product is to limit the need to physically move a vacuum cleaner over the carpet. The user still needs to pick up large objects before running the device. Design requirements. The devices must be able to move/pick up objects weighing up to 1 kilogram. The devices must be able to operate and communicate wirelessly. The battery must be able to power the device for at least 1 hour on a full charge. The devices must be able to maintain a sound level below 70 decibels during operation. Devices must be able to be capable of autonomous charging cycles. The devices must be equipped with a storage container with a volume of at least 1.5 cubic feet. The devices must be capable of sensing objects within 5 feet of themselves. The devices must be equipped with a way to clean messes related to spills and stains. Product description. Included are descriptions of each individual robot's function, as well as how they will work cohesively to complete their task. Detailed sketches of each robot and descriptions of their moving parts are included in the next section. The project schedule with a detailed Gantt chart is listed in the document, as well as backup options to satisfy different design requirements. There will be 5 robots, each with a different purpose. Alicia Intencio is responsible for a docking station/charging station. This device also contains the ability to program a day of time that the robots can be designated to clean. Steve Slocum is responsible for the sweeping robot. This robot is designed to clean up lints, dust, crumbs, materials that are currently cleaned up by the use of a vacuum cleaner. Can be used on either carpet or hard flooring surfaces. Trey Chaffin is responsible for the mopping robot. This robot is designed to clean up spills, mud, and smudges on hard flooring surfaces. Can act as a wet Swiffer in the absence of any visible mess. Mario Parks is responsible for the picking up robot. This robot is designed to pick up small to medium-sized objects on the floor left behind by children, husbands, wives, or pets. Robert Layton is responsible for the storage robot. This robot is designed to act as a mobile storage bin. It follows the picking up robot and works in conjunction with one another to declutter living spaces. The robots move independently from one another, but work in unison to complete their task. The goal is to clean and declutter the house. With the 5 mobile robots, that goal should be attainable. The first robot we'll be discussing is a sweeping robot made by myself, Steve Slocum. This is the 3D design of the internals of the sweeping robot, the 9-volt battery, and the Arduino circuit, as well as the interior storage container and the wheels. This is a side view of the robot, again highlighting the wheels. This is the exterior of the robot with the black bumper and the power button included on the top. This is the underneath of the sweeping robot with the wheel axles and the vacuum sweepers. This is the sweeping robot's Arduino circuit. You can see there's a 9-volt power source, on-off button, DC vacuum or DC motor for the vacuum, right and left motors for the wheels, an obstacle detector to detect obstacles within a set parameter, an obstacle notifier to let you know when the sweeping robot comes into contact with an object, it's going to perform a movement, whether it be forwards, right, left, or backwards. This is the sweeping robot's code and a provided link to a YouTube demonstration on how the Arduino code works when prompted. Here's a brief demonstration of how my Arduino code works. So you depress the power button, it will kill power to the circuit. When it is removed, the circuit has power again. As you can see, vacuum is running. The motors for the wheels are working. Going forward, and click the obstacle detector within a set parameter. If I am on the right side, it should prompt the robot to go left. Let that clear. It'll continue to go forward. Same thing on the left side. Should prompt the robot to turn right or left. And then once it goes forward, I'll try to see if I can get it to go in reverse. Oh, you can go in the right direction. And there is reverse. There's a cycle of operations. The robot will continue to run until it's either full of debris or the batteries no longer has any power. And that's it.
I'm Alicia Tencio, and I'll be talking about the docking station. This unit will serve as a central hub and charging station for the other units in the swarm. It's programmed by the user to tell the swarm when to go out and perform their respective tasks. It remains stationary most of the time, except when one of the robots from the swarm loses battery power and isn't able to make it back home. When that's the case, the docking station will go seek out the dead robot and charge it enough to complete their tasks, or tow it back to the home position if the battery is too far drained to accept a quick charge. Here's a few views of the mechanical design. The figure on the left shows the top view of the unit. The gold ports on the 4 sides are connectors used to charge the other robots. The red squares on each side are distance sensors, and the round loop on the back can be used for towing. The bubble in the center is where all the electronic components are housed. The 2 smaller pictures on the right show the front and rear wheel axles, which will allow the robot to move freely through the user's home. You'll notice that the wheels on the unit are rather large in order to navigate different flooring types throughout the home. The mechanical aspect was changed once through the design process because it was originally going to be a stationary unit, but in order to make the swarm more efficient, it was designed to move. Here's some information about the circuit, and this robot relies on user input to tell the swarm when cleaning should begin. The user input is communicated to the swarm through the green LED. The illumination signals the swarm it's time to start their work. Once all units in this swarm have left home base, the docking station monitors power levels of each robot using the blue LED. When it receives a low power signal from any of the robots, the motor turns on to navigate to the desired unit. The docking station then relies on the distance sensor to tell it when it's close enough to connect with the other robot, at which point the motor stops. The left figure shows the actual Arduino circuit, and the right side shows the circuit schematic. This portion of the design was originally going to have 2 motors, but in order to save on budget, a single motor was used to power only the rear wheels. Here's an activity diagram showing the logic for the Arduino code along with the actual code. The code begins with a request for user input. For the sake of this presentation, 1200 is when the cleaning will start. The user tells the docking station to start cleaning at the designated time. When the time is equal to 200, the condition becomes true, so the green LED illuminates, telling the other units to go out to accomplish their tasks. Then the docking station begins monitoring for low power signals from the swarm. If a low power signal is detected by the blue LED, the motor is triggered to seek out the dead robot. Once the docking station approaches the other robot, it relays on the distance sensor to let it know when it's close enough, in which case the motor stops to allow the 2 robots to connect with each other. And then now I'm going to show a quick demonstration of the code working. So start the simulation. And the robot's going to ask the user for their input, asking what time do they want to start cleaning. And then, as I said, in this case, it's going to be 1200. So they want to start cleaning at 12 o'clock. We send that information to the robot, and then the green light quickly illuminates to tell the swarm it's time to go out. And then the swarm starts, the robot monitors the swarm using the blue LED, and then that blue LED will trigger the motor to start working, and then the distance sensor will tell the docking station when it's close enough to connect with the dead robot. So you can see the distance sensor here, and once it's within the 5 inches, usually it would be less than like 2 inches, but for this demonstration, it's less than 5 inches, and the motor stops here. And the next robot will be the mopping robot.
All right, so the next robot, like Alicia just said, is the mopping robot, which was designed by me, Trey Chafin. So as far as the mopping robot, it's a fairly simple design. There's a section on the front highlighted here in red where distance and light sensors are located, which will be used to determine where walls are, when to turn, and when it's time to work. This is a bottom view here that shows highlighted in red an actuator that sprays a cleaning solvent onto the ground, and yellow, which is a stationary a mop brush. As far as the circuit design, on the right here we have the internal view of the robot. Red is the Arduino circuit, the light blue is the motors, and the orange is the axles. And so over here we see the circuit mapped out. We have a power source, we have a motor for the right wheels and a motor for the left wheels, as well as a servo that powers the actuator for the cleaning solvent, and a distance sensor that measures the distance to walls and other objects. Our activity diagram just shows a quick overview of how this robot works. If the robot is signaled ready to work, then it moves on. If not, it waits till it gets that signal. The actuator and motor start when it's signaled to work, and it keeps driving forward until it sees an object in its path. If it doesn't, it just keeps driving forward, and if it sees an object in its path, it will turn to find a clear route. And here's the code that shows how that's going to work. All right, so now for the Arduino simulation of my code. When the robot gets the signal to start, the motors fire up and the actuator starts turning to spray solvent. And then when it sees an object in its path, one motor stops while the other keeps running, which would rotate the robot until it sees an object, sees a clear path in front of it again, and it'll start moving forward. So basically, it'll turn until there's nothing in its way, start moving forward again, and if it sees something else in its way, it will turn more, which would help it to avoid obstacles.
Thank you very much. My name is Mario Parks, and I was responsible for designing the lifting robot. And as you can see here, this Tinkercad model. Up first, there's a ramp, which also houses the distance sensor. Originally, one of the design concepts involved having arms, with actuating motors in order to physically lift items up, but for simplicity's sake and to best satisfy the requirements, a conveyor belt and ramp system was decided upon. And that conveyor belt system has two motors, one for the slanted conveyor belt and one for the flat conveyor belt on top of the unit. Inside of the main body, there are 4 individual wheel motors, so 1 motor per wheel. And then in the rear is an assembly with the charging port and the light to indicate to the storage robot when it's time to come pick up an item. Here's the Arduino circuit and code. There are the 4 individual motors, as well as the 2 servo motors for the conveyor belt. And in the front is the sensor for detecting objects, targets, and obstacles. And here's that same circuit. And just for a quick demonstration, I will show how it works. As you can see, all 4 motors are moving forward. All 4 wheeled motors are moving forward. And when it detects an item to pick up, the conveyor belt motors turn on as well. Again, for simplicity's sake and to minimize the moving parts, it is the actual motion of the bot that moves forward, slides the item to be picked up onto the ramp, and then it is carried onto the back by those motors. Here's the overall activity diagram, and if we just focus on the lifting bot here, essentially what happens is once it detaches from the hub bot, it scans the entire area of the cleaning, of the area to be cleaned. And when it detects an object to be picked up, it notates that location until it has completely scanned the entire room, at which point it goes back to pick up the items and then signals to the storage bot to meet at a predetermined location in order to remove those items from the cleaning field. And to further demonstrate this, I coded a simulation in MATLAB. So first, these are going to be obstacles, so chairs, tables, lamps, potentially people. These are wet messes to be mopped up by the mopping robot, and then dry messes, particulate messes to be swept or vacuumed by the vacuum bot. And then lastly, items to be picked up by the lifting bot in coordination with the storage bot. So as you can see here, they move on different paths to scan the room, avoiding each other and objects or obstacles while notating their respective targets. Now that they've completed scanning the room, the mopping and vacuuming robot move to eliminate their items, and the lifting robot goes to pick up the items. And now that the lifting robot has picked up the items, it moves to the side, signals to the storage robot, which was still connected to the hub bot this time, waiting for the signal. And it goes to pick up those 2 items and remove them from the cleaning field. And next up is Robert to discuss the last robot.
All right, my name is Robert Layton and I designed the storage bot. This is my 3D model of it. This is a side view and the circles here, one of these is a PIR light sensor and the other is a distance sensor. You can see on top it has a basket that can hold the objects that are picked up by the lifting robot, and it has 2 servos so it can tilt the basket and dump the load. On the back it has a set of charging pins to charge off of the central control bot. And then here's another front view. And then this is a view if you were looking at it from the bottom with the lid off, and there's a battery, a breadboard, and an Arduino inside of it. This is a picture of my circuit. We have 4 DC motors, which are for the wheels. The left side is all controlled simultaneously, and the right side is controlled simultaneously for the wheels. A 9-volt battery supply to go through the L293D chip. We have green and red LEDs around for different signals to the other robots. These are the servos that will tilt the basket, a distance sensor to detect how far away the other robots are and how to get to them, and then the PIR light sensor to detect the other lights. This is a copy of my code. This is the first 121 lines, and then this is the rest of it up into 181. And then I will perform a quick demonstration in Tinkercad of it working. So again, here's another quick run through of my code. And to begin the simulation, the robot, as you can see in the serial monitor, it is awaiting the lifting bot, and the DC motors on the left are going forward and the ones on the right are going backwards, so that it is spinning around and constantly looking for that LED on the lifting bot. So when it detects the LED, this is it detecting it. The lifting bot has an object. So the bot will stop, and then it will begin driving forward towards the bot. And here you can see how far away it is. So as it begins approaching, it gets closer and closer and closer to the bot. And then when it gets to it, stop. There we go. I think I went too far with the circle and it read 100. So once it gets up to the robot, it says arrive to the lifting bot. And now it is awaiting for the object to be loaded. And to indicate that to the lifting robot it's ready, the green LEDs have been illuminated. And it waits a little longer. The object has been received. So then it'll let the bot go away. And now it's circling around again, spinning around, looking for the storage bin. And the storage bin has an LED on it. So it'll be the same method of detecting that with the sensor. Once it sees it, the storage bin has been found. It'll stop for a moment, and then it will begin driving forward back to the storage bin. And then once it has arrived, it will stop, and then the servos will actuate to dump the load. It'll wait a second, make sure all the objects have come out, and then it'll close the basket. The load has been dumped. And then it will begin its routine from the beginning again, looking for the lifting bot. And then one other part of this code is if the battery were to get low, it'll signal to the control bot. So just to simulate that, I'll remove the 9-volt battery. And here you can see the battery is low and it's awaiting charge, and it has illuminated the red LEDs to indicate to the bot that it needs to be charged. And here's a picture of my activity diagram. Basically what I just explained previously. The component parts based on Amazon pricing: the Arduino Uno's $23.50, the gear motors are $3.25 each, the distance sensors $2.72, 4 sensors $7.50, the LED bulbs are 3 cents, the charging ports are $3.14 each. The 3D printer filament is $25 a roll. The conveyor belt is $4 a foot. Sweeper brushes $7 each. Assorted nuts and bolts, about $40. Wheels are $7.98 for a 4-pack. Wheel axles are $1 each. Assorted wires are $6.98 for a 120 count. And the Arduino LCD display is $6.99 each. From an entrepreneurial aspect, similar products available on the market are Roombas and other similar robots. Our product adds value by performing many tasks together, tidying up and cleaning. Can be scheduled to run when you are not home and is small enough to not be in the way and is quiet enough for any type of household. In summary, our goal was to design 5 robots that work synergistically with one another to maintain cleanliness on the floor level of living spaces. That was achieved during this project. Over the last 7 weeks, we've learned how to 3D CAD a prototype design a rather complex circuit in Arduino, while also learning the basic foundation of 2 coding languages. We had to work as a team while being separated by thousands of miles, also being respectful of differing opinions and skill sets. We managed our time effectively, having many Zoom meetings to brainstorm ideas and designs. It would have been nice to have done this project with our team in person. We were able to achieve a lot separated. We may have been able to achieve more together. And this is a copy of our references. And that's it.